folks, so yesterday I didn't get quite as far with you guys as I did with the first two periods. Unfortunately, they did get through these two questions, but that's okay. We'll make it work. So we ended yesterday by talking about finding domains of functions algebraically. This one is a square root bar, and what we said was there are certain things you can't take the square root of, and those things are negative numbers. No square roots of negative numbers, right? So how do you make sure you don't take the square root of a negative number? What we did was we took the inside of the square root bar and made sure that it was positive, greater than 0, or equal to 0. That guarantees not negative, got it by itself, boom. The only other structure that we concern ourselves with right now that has a domain restriction is fraction bars. There's one rule about fractions that can never be broken, and that rule is do not try to divide by 0. The bottom denominator of a fraction cannot be 0, so it'll look like this. Whatever wants to be on top, nobody cares, but the bottom is not allowed to equal 0. This would be the big no-no for fractions. So the only time that this can even be an issue is if you have x's in the denominator. Because if you have x's in the denominator, you have a denominator that might try to equal 0, and we have to stop that from happening. So right here, nobody cares what's on the top of this fraction. Unimportant. All that matters is that there's an x minus 5 in the bottom. X minus 5 does have the opportunity to equal 0, so we have to make sure that does not occur. So you say x minus 5 never equals 0. You just make sure that that occurs. So you would just add 5 to both sides to figure out what number would cause you an issue. I know you could probably just see it, but still. You find out that x cannot be the number 5. It could be anything else though. That means x can be less than 5 or x could be greater than 5. So that's one way of writing that domain. X is less than 5 or x is greater than 5. But if you wanted to put that as an interval, this is actually two different intervals. You're going to have an interval for less than 5, you'll have an interval for greater than 5, and we will need to string them together somehow. New symbol for you more than likely. So how do we say all the numbers less than 5? If you're on the number line and you're talking about less than 5, you're talking about 0, negative 10, negative 1 billion, negative, 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 all the way out to the far left is negative infinity. You can never bracket an infinity, but negative infinity is the absolute smallest thing we can imagine, and we'll be coming all the way up to positive 5 and not including it, and that's why it's a parenthesis, not a bracket. Now x is greater than 5 is 5, 10, 20, 30 bajillion, you know, all the way up to positive 1 or positive infinity. So 5, comma, positive infinity, everything goes from small to big. When you have to have more than one interval strung together, because they don't overlap, the way we're going to string those together is with that symbol. That's a U, without the stick on the end. It's called a union. And union literally means, oh, and also this stuff. So this stuff, oh, and also this stuff. That's what that means. Are we all comfortable with how to find a domain algebraically? Unfortunately, there isn't any in the homework this year to practice. And this year is the, what, 25, 26 school year, right? Okay, next year, 26 and on, there are questions like that in the homework. I added them yesterday to make sure that the homework was good. So I'm hoping that I'll have time after the lesson is ended, so to speak, to just throw a couple on there. Okay, we'll see. We'll see. Fingers crossed. We are a little bit behind, but. Square root bars, whatever's underneath it, greater than or equal to 0. Bottom of a fraction, not equal to 0. Those are our only two rules. Everybody's cool with that, you said. Great. The only other way that we can restrict a domain is if we run into some kind of situation that doesn't make sense in the real world. Like this last example. It says a of x equals 4x squared. Where a of x represents the area of a square and x represents the length of its side. If this is a real square with length of its side, what must be true about the length of any object, Jordan? Well, that's true for all squares, but if it's in the real world, what must be true about those lengths? Hold on. Crap. If I was looking at my roster, I know your name. But, Nolan. Yeah. Yes, Nolan. Okay, I figured it out. Without looking at my roster, let the record show. You can't see that on camera, but I did not look at the roster. Nolan, what do you know about the length of a square if it's a real square? They're all the same. That's what Jordan said, but what has to be true about those lengths that are all the same? Come on, this is something really obvious because it's a real world square. They have to be positive, folks. It's a square. Like the sides have to be a positive length, right? Negative lengths don't make sense. Which means literally x has to be greater than 0. It is that simple. See, it was so obvious, everybody was afraid to say it. It has to have a positive length. Is this a correct domain? Yes, but we wouldn't write it like that. We would write it like this. You can't have a length of 0. If you have a length of 0, you don't have a square. And there it is. All right. So that's how we find domains algebraically. Let's move on to other properties of functions, relations, and things like that. So we've got a box here with some more vocabulary. We will work on visual and verbal vocabulary again. Yesterday we talked about relations, and a relation is any kind of rule or anything like that that will turn one thing into another. It turns an input out into an output. Typically turns an x into a y, right? Anything that could be done in math could be undone. So if there's some rule that turns an x into a y, then there must be an inverse rule that turns that y into an x that will literally undo them, change the order, so to speak. So an inverse relation is a rule or an equation that maps the range, typically y's, back to the domain, typically x's. Makes the domain and range switch places, okay? Basically an inverse relation, that word was supposed to be relation, an inverse relation undoes whatever it was that the original relation did. That's all it does. It's like addition undoing subtraction. Those are inverse operations. Inverse relations switch the x's and the y's back to the way they were before the relation worked. Graphically, what does that do? Well, graphically, an inverse relation, an inverse graph, will be the reflection over the line y equals x. And you should have done reflections over the line y equals x in geometry. If you've already completed geometry, I have a handful of students this year that are in geometry right now. You will do reflections over y equals x in geometry. But reflecting over y equals x has the exact same result of just switching your x's and your y's. What does that look like it does to a picture? Well, it looks like it turns it 90 degrees. Now we don't rotate in algebra because it creates not functions, so we don't actually do rotations, but that's what it looks like it does. Turns it on its side. Cool beans? Awesome. Okay, now, if the inverse of a relation happens to be a function, then we will call it an inverse function, and the symbol for inverse function, let's just assume the function's name was f. The inverse function would look like this, f inverse of x. It has a little superscript of -1. I know that looks like an exponent. It's not an exponent. And the way that you can tell that it's not an exponent is because f is not a number and f is not a variable. F is the name of a function. So that little superscript of -1 up there says f inverse. If you say f to the -1, I'll say you mean f inverse. If you say f -1, I'll say you mean f inverse. I'll correct you because we have to be very accurate with our words in algebra. So we're about to run across some stuff that's really special. Let me draw a picture. You don't need to do this. I'm going to draw a picture for you though. I'm going to draw a parabola. This parabola, actually, there's how many of you in this class? 30 of you. And you're not all here today. I got 2 people missing, so I got 28 of you. I'm looking for 28 voices, and I'm just looking for a yes or a no, and it would be great if we can hear those 28 voices in the video, because then it makes me seem like I'm a stupendous teacher. And that is, class, is this a function? Yes. Yes, of course it is. This passes the vertical line test. Okay. Now, I told you that switching the x and y, it looks like it turns its graph on its side, right? Let me turn it on its side. Looking for those 28 voices. Is this inverse graph, is this a function, class? No. No, it's not, because it fails the vertical line test. Now, occasionally, though, inverting something produces another function. So if I had a function and then inverted it, and the inverse is also a function, then we have what we call one-to-one functions or one-to-one relations. Why is it called one-to-one is the question. Definition of a function is, for every input, there's exactly one output. Okay? So if it's a graph of a function, for every x, there's exactly one y. But if the inverse switches the x and the y, and the inverse is also a function, then I've said for every y, there's also one x. For every x, there's one y. For every y, there's one x. And that is why they would be called one-to-one. This one is not one-to-one, because even though this is a function, this is not. Okay? Let me draw something that is one-to-one so you can see what it looks like. This graph is one-to-one. This passes the vertical line test. This also passes the vertical line test. Remember what I told you yesterday, the day before? No smooth curves have vertical portions. It's really steep, but it's not vertical. Cool? So, function. Function. Since this graph and its inverse are both functions, this would be one-to-one. One more graph. Not a function. Its inverse is a function. Okay? Also, not one-to-one. One-to-one requires both of them to be functions. Cool? Now, the way that we could tell that this thing was a function when it was turned sideways is because this image right here, this is passing the vertical line test, correct? That's how you know it's a function, by looking. Let's pretend that this orange pen is that vertical line test. Ready for this? Now it's not a vertical line, now it's a horizontal line. I could have used this horizontal line to tell that the inverse graph would have been a function. And I could use that horizontal, let's see. Not a function because failing the vertical line test, right? Oh, look at that. A horizontal line that would have told me the inverse was not a function. Not a function because it's failing the vertical line test, but I could have used a horizontal line to see that the inverse would have been a function. Because switching the x and y values makes a graph turn on its side, we can use the horizontal line test to see if the inverse of something is a function. Okay. So let's kind of pull it all together. Horizontal line test, or excuse me, vertical line test tells us if something is a function. Horizontal line test tells us if something inverse is a function. Pass both tests one-to-one. Comfortable with all that stuff? That was both verbal and visual vocabulary. Tried to hit you with both. All right. Let us take this wacky thing that I've created for us and sketch its inverse. This is a function. It passes the vertical line test. Its inverse is a function. It passes a horizontal line test. That is one-to-one. But that's not what this question is about. This question is about actually sketching this thing's inverse. The first thing I'm going to do is I'm going to draw the line y equals x as a dotted line. Y equals x goes through 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. There. There's the line y equals x. Reflecting over the line y equals x will get me my inverse graph. Now I could just try to eyeball this, I could. Or I could be very precise and I could take every pretty point that this black graph goes through, write down those coordinates, and switch the x and the y. And that's what I want to do to make sure this is highly precise. Every one of its pretty points. Here's the first pretty point. By the way, there's 6 pretty points. That one is at -4, -4. My next pretty point from left to right is right here at -3, -2. Then I'm right here at negative 2, 0. Go around this little curve, your next pretty point, 0, 2. Only 2 more pretty points. One right there at 2, 3. And lastly, one right here at 4, 4. I mean, the graph does go past 4, 4, but it's not a pretty point, so I didn't write it down. Here's what we're going to do. We are going to reflect over the line y equals x, which will have the result of switching the x's and the y's. So I'm going to write all 6 of these coordinates, but I'm going to switch x and y. So I've got negative 4, negative 4. Well, that point didn't move. Well, that makes sense because it was on the line of reflection. Then this one will become negative 2, negative 3. This one will be 0, negative 2. This will be 2, 0. 3, 2. And lastly, the other point that's on the line of reflection, so it will not move, 4, 4. Going to plot these 6 green dots and connect them to the best of our ability. So we started here, which you can't really see that I put a green dot on that black dot. Then negative 2, negative 3 here. 0, negative 2. In my black image, those first 3 black dots are connected by a straight line, so I'm going to do my best to make that a straight line. Then my black one went around this little curvy thing. It actually is 1/4 of a circle. That next point is at 2, 0, so I have to try to connect this point and this point with a 1/4 of a circle to the best of my ability. That's pretty close. 3, 2, and 4, 4. But the picture does go through and hit the halfway point on the next one. So I'm going to connect my dots, and it's something like that. I missed it a little bit. I'm off just a little bit up there. But I'm hoping you can see that if you were to rotate your paper a little bit, or just rotate your head a little bit, those 2 pictures are reflections of each other over the line y equals x. Maybe like a UFO. But there it is. You have a test question coming up soon that gives you the image of a graph and says, and it's multiple choice, which of the coordinates below is on the inverse? And that would mean that one of these would have been the answer. So all you have to do is write down all the pretty points, switch x and y, and then figure out which one of them is an option choice. How many of your teachers tell you exactly what's going to be on their test? Like exactly what's on the test, okay? I want everybody to do well, but this first test requires a lot of understanding and not a whole lot of doing math, like doing math, right? It's a lot of understanding math. And just to really drive home this point, if I told you that the coordinate 2, negative 3 is on your function, and then I asked you what's on your inverse function, you should be able to quickly and easily tell me negative 3, 2. See, there's no work to be done here. You understand that an inverse switches the x's and the y's, switches the domain and the range, switches the inputs and the outputs. Okay? How do you guys feel about that? It's okay? They can't see head nods and thumbs up on the camera, but I get it. Everybody says they're okay. Yay! Okay. So like I said, there's 28 of you, right? We ready for me to move the paper? Nobody will panic? Okay, I just want to make sure everybody's finished writing. There are 3 graphs down here, graph 1, graph 2, graph 3. 1, 2, 3. And what I want in a moment, when I ask the question, is I want every one of you to tell me which one of these is 1 to 1. Hey class, 1, 2, or 3, which one of these graphs is 1 to 1?
3.
3. This graph is 1 to 1. And how can we tell? All right, so we're going to write 1 to 1. Because, B/C for because, passes the vertical line test and the horizontal line test. So because it passes both line tests, I can tell you that yes, this is a function and its inverse is a function. It's the only one that passes both line tests. 28 of you. Is this a function? No, it's not. All 28 of you. Is its inverse a function? Yes. Yes, it is. Okay. Because this passes the horizontal line test, I know its inverse is a function, but this clearly fails the vertical line test. So this, I didn't mean to write in green again, or blue. I meant to write in green is what I meant to say. So not a function, but inverse is. So it's not a function because it fails the vertical line test. The inverse is because that passes the horizontal line test. All 28 of you. Is this a function? Yes, passes the vertical line test. All 28 of you. Is its inverse a function? No, fails the horizontal line test. Function, because, passes vertical line test, but inverse is not, because it fails the horizontal line test. So you've now seen examples of something that is a function whose inverse is. You've seen something that is not a function, but whose inverse is. So both function, only originals function, only inverses function. You've seen all three. Cool beans? So that is a property of functions and relations. If you are comfortable with that, then we'll go to the next property of relations and or functions. And we'll actually start focusing on just functions when we talk about symmetry. Now there are lots of kinds of symmetry in mathematics, but there's a couple that are more important than others. In this first chapter, and in this first chapter only, I will test you on these very broad kinds of symmetry. This first very broad kind of symmetry is called line symmetry, and a graph has line symmetry if it can be reflected over a vertical line so that its two halves are mirror images of each other. This graph that I drew a minute ago has line symmetry, specifically this vertical line. That vertical line is known as the line of symmetry or the axis of symmetry. Cool with that? And every point on one side is the same distance from this line as its reflection. So these 2 points here and here, these 2 points here and here, they're equidistant from that axis of symmetry. That is an example of something that has line symmetry. This does not have line symmetry. The inverse has line symmetry, see? But this doesn't. Okay? Here's a parabola showing you line symmetry for that parabola. So it stands out better. Another very broad form of symmetry is called point symmetry. A graph has point symmetry when it can be rotated half a circle around any one of its points. Just pick, if there is a single point that you could rotate that thing around half a circle and it land on itself again, that graph has point symmetry. This one happens to have point symmetry right there at that point. If I turn this half a circle, it'll land on itself and look like the exact same graph if I spin it around that point. Cool with that idea? All right. So that graph has point symmetry. And this graph has point symmetry. Technically, this graph has point symmetry. But these two have very special types of point symmetry. The point that they're symmetric around is the origin. So sometimes you'll see it called origin symmetry, but that just means point symmetry around the origin. Now these words here, they get a little convoluted, and really all they say is, if you connect this dot and this dot through whatever the point symmetry is, this little piece is the same length as that little piece. And those little hash marks that I used, those you learn about in geometry, it's just showing you those two segments are the same length. That's all that is. Okay. Those are very broad forms of symmetry. Line symmetry, you could fold the graph in half along a vertical line. Point symmetry, you could spin the graph half a circle around one of its points and land on itself. The specific kinds of those symmetries that we will talk about all year are in this box down here. An extremely special form of line symmetry occurs if the axis of symmetry / line of symmetry happens to be on the y-axis. If the y-axis is your line that you are symmetric around, then what you could say is you are dealing with an even graph. Usually we would say even function. If you shift this thing up and down on that y-axis, the y-axis is still cutting it perfectly in half left and right. So shifting it up and down would not change the fact that it is an even function. Shifting it left and right would. This is not an even function because its axis of symmetry is not the y-axis. Comfortable with the words and the graph of that explanation? Okay, fantastic. Then this is what we would use to check for even symmetry using algebra. Here's what this says. Replacing x with negative x has the same result as did nothing. So I'm going to write that in. Substituting negative x does not change the equation. And we have examples of that on the back. So you will replace all of your x's with the negative x, you do a tiny bit of math, and you will see if something changed. And if it looks like absolutely nothing changed, you found yourself an even function. A very special type of point symmetry happens when that point of symmetry is the origin. If point symmetry occurs at the origin, then what you have on your hands is an odd function. This graph has point symmetry, but it does not represent an odd function because that point symmetry did not occur on the origin. This is nearly the same graph, but you will see its point symmetry does occur on the origin. And because its point symmetry does occur on the origin, that is an even function. Oh, I misspoke, an odd function. That is an odd function. Another way that you could recognize odd functions graphically is by reflections. If you reflect this upside down, so it does this, boink, you'll get a graph that looks like that, right? Now imagine you reflected it left-right, boink, the exact same image. So if reflecting up-down gets you the exact same image as reflecting left-right, you found an odd function. This one is an odd function. It has point symmetry at the origin. This one is an odd function. It has point symmetry at the origin. This one has point symmetry, but it is not an odd function. And earlier today someone said, if something is not even, is it odd? Or if something is not odd, is it even? No. Something could be even, or it could be odd, or it could be neither. This is neither even nor odd. This is neither even nor odd, okay? But the algebra for this one seems to be the one that's the toughest for people to do. The algebra says you replaced all your x's with a negative x. And after you cleaned it up, it looked like you just multiplied by -1. Substituting negative x looks like you just multiplied by -1. And that will be the algebraic tests. Both algebraic tests require you to substitute in negative x and see what happens. That's what we'll do on the back. Three examples. And these would be the only kinds of examples that in the homework you actually had to show some work for. The rest of them are just like yes, no's, and things like that. You know what I mean? Whereas these, you'd have to show a little bit of work. I'll use color. That way you can see me substituting in the negative x. Part A. Everywhere I had an x, I'm going to stick a negative x. Using parentheses. Remember what we talked about in the prereq review week. Anytime you substitute a number, you really should be using parentheses. So here is me dropping in negative x on the left and negative x on the right. You know, whatever you do to the left, you have to do the right. But I do need to clean this up a little bit. I need to simplify it. My set of parentheses is squared. That means that set of parentheses times itself. So literally that means negative x times negative x. So what kind of number do I get when I multiply two negatives, 28 people? Positive. Okay, so we know it's going to be positive. And when you square a number, you get to multiply it to itself and get a new number, but x is a letter. So if you do x times x, you're going to get x squared. And, oh, there's the original equation. That's what I got after I substituted in negative x. This is literally the original equation. So since f of negative x equals f of x, this is an even function. You see, plugging in negative x and cleaning it up looks like I didn't do anything at all. That means it's an even function. Students are pretty good at identifying even functions because they're pretty good at noticing that nothing changed when they plugged in negative x. But if you have any question at all, please put that hand up in there. Not to mention it makes a great video because then I get to answer student questions on the video. But you don't have to, but it makes for good YouTube. You know, like, subscribe, merchandise in the link below in the description. You know what I mean? You guys laugh, but I have like 450 subscribers. You know, like I'm important. And I do have a merch store, but not on YouTube. You'll never find it though, because I didn't use my name. I didn't want my students to be able to find it. I made up a name. I even made up a state where I live. Just faked it all. But anyway, okay. If there's no questions, then let's go on to example B. I'll use blue for this one. B. Oh, see? B for blue. The letter changed. That's just because it's a different function. That letter that's in front of x is just the name. So this is function f, this is function g, this is function h. It's just its name. But we are still going to have to test for this special type of symmetry by substituting in a negative x everywhere I had an x. So everywhere I had an x, I'm going to open a set of parentheses, and then I will substitute in that negative x. If I fill the parentheses with negative x on the left, I better fill those parentheses with negative x on the right. At that point, all we have to do is follow the order of operations, simplify whatever we can simplify, and then look at the result. We just talked about what happens when you square, I'm shaking. We just talked about what happens when you square negative x. You get x squared. But negative 2 times negative x, you guys told me when you multiply two negatives you get a positive, this is going to be plus 2x, and nothing happened but the minus 2. So the question is, are the original function and the new one when substituting negative x exactly the same? You guys could just shout it out. Are they exactly the same? No, of course they're not. So since g, that's the name of the new function. Since g of negative x does not equal g of x, this is not even. But it might still be odd. So unfortunately, because it's not even, we will have to do a little bit more work to check to see if it was odd. The odd rule, don't worry, I'll come back, required me to see what multiplying my equation by negative 1 was. So I am going to take my original g of x, and I'm going to multiply it by negative 1. I'm going to multiply by, and if I go back to this rule, I know there's not a 1 written there. Whoops, you can't see it. I know there's not a 1 written there, but I hope you all know that it's implied that there is. I could even sneak. It's there. Okay, it's there. Let me go ahead and multiply both sides by -1. Good? Does that work? No, it does not. I did not multiply my right side by -1. I multiplied x squared by -1. How do I make sure I multiply the right side by -1? Parentheses. You guys are going to have to get used to using parentheses a lot at this level of mathematics. They are super important. There. Now I've multiplied both sides by -1. Let's see what the result is. You distribute that -1. You get a negative x squared, a positive 2x, a positive 2. So now the question is, did switching negative x give you the same result as multiplying by -1? Are these the same? No. So g of negative x also did not equal negative g of x. So it is not odd. This one has neither even nor odd symmetry. And those of you that do some reading might have caught that in my directions there was a typo. I must have been thinking about Minecraft. That says nether instead of neither by accident. Oops, just pretend it says neither, okay? Looking for odd symmetry tends to be the one that stumps my students. So if you have any questions at all about the process, please talk to me. Nobody likes me, nobody wants to talk to me. Got me. Okay, I'm good. It's all right. Then let's move on to example C. Example C is big time scary because it's got a fraction. That's sarcasm. It's not scary at all. Fractions are our friends. Both tests, even in odd symmetry, require me to substitute x for negative x, or negative x for x. I said it backwards. Replacing all my x's with negative x. So everywhere that h, function h, had an x, I have a set of parentheses. And in those parentheses, I am going to plug in my negative x. Got to do it on the left and the right. But just like examples A and B, I do need to clean this thing up a little bit. The denominator is easy because we've talked about negative x squared twice already. Negative x quantity squared is just going to give you positive x squared. So my denominator is going to be 4 minus positive x squared, or just 4 minus x squared. But in the numerator, negative x to the third power means negative x times negative x times negative x. If you multiply 3 negative numbers, lots of voices, what kind of result are you going to get? Negative result. And then x times x times x is just going to be x to the third. So what we have is negative x to the third. So now you get to ask yourself, did plugging in negative x change anything at all? Yes, it did. So since something changed, h of negative x is not the same as h of x, so it is not even. But then what you need to do is ask yourself, is it possibly an odd function? So you take your equation, your h of x, and you multiply both sides by -1. Remember, when you will multiply a side by -1, you should probably use parentheses, at least on the right side, because there's some stuff going on over there. So let's take our h of x, and let's multiply both sides by -1, but the right side I used parentheses because I got a lot going on. This next question is going to be a yes or no question, and I'm looking for 28 voices. I already know what kind of answer I'm expecting to hear from you, but let's just see what happens. Class, on that right side, I'm multiplying by -1. I'm looking for you to say yes or no. Do I multiply the -1 to the top and the bottom? So it was a mixed bag, and it was much quieter than before. I did hear some yeses, and actually all I heard was this at the end. The answer is no. You never multiply the top and the bottom by a negative number when you're multiplying a fraction by a negative number. If you're multiplying a fraction by negative, the negative either goes to the top or to the bottom, but never both. That's why when you have a negative slope, you choose either the top is the negative number or the bottom is the negative number, but never both. Now let's be really clear here. If you're multiplying a fraction by a number other than a 1 or a negative 1, this is only to the top. And the reason why it's only to the top is because the implication is that this is a 2 over 1. But if it's a negative 1, you wouldn't know if you did it to the top or to the bottom. I just wanted to be clear about that. So there actually, it could be written several different ways. You could put it on the top. Which, by the way, shows us that this is an odd function. Or you could put it in the front. These are all the exact same fraction. I recognize those as the same. I mean, the answer is it's odd, because this substitution got us this result. But I want to show you other ways this fraction could have been written. Here it is on the top. Here it is on the front. What if you multiply it to the bottom, though? What happens if you multiply 4 minus x squared by negative 1? If you distribute that negative 1, you get negative 4 plus x squared, right? Which is this. So you have to watch out, because it might have been sneakily an odd thing and you didn't recognize it because you weren't comfortable with multiplying fractions by negative 1. So be really careful. But right here, I need you to see that this and this are exactly the same. Because of that, we get to say that h of negative x is equal to negative h of x. So this is an odd function. And with our last few moments, I get to ask, are there any questions I can answer about how to test for these two types of special symmetries? In your homework, you will have to show this work. You don't have a whole lot of space, write small. If there are no questions on it, then I will say, thank you, nerds, and we call it there.